I have a lot of tasks to accomplish, and I can see that Brian has just added a new one to the list: optimize for cost. To make sure we complete this job and stay below budget, validating the function of the entire pick and place mechanism is required. I'll be simulating the motion of the arm, picking up the soap bag and placing it into a box. Creating a working model will provide the torque values necessary to size the motors appropriately. Hopefully, I can discover some easy ways to optimize the system and keep within budget. The model I received from the design team is properly assembled, but I need to make the motion more realistic. I'll add one more mate that'll simulate the path the soap bags will take as they're being lifted from the conveyor and placed into a box. Starting from a new sketch, I'll draw a spline to represent the path. Now to add some dimensions and make sure the soap bag clears the leading edge of the box. The path mate allows me to connect a vertex on the soap bag to the spline sketch, locking it into this ideal path. No more guesswork, no physical prototypes necessary. Adding a path mate defined what I want the motion to look like, but designing for proper cycle duration requires further simulation. For that, I'll enable SOLIDWORKS Motion. I'll need to add a motor to drive the arm. Wow, that's easy. There's even a path mate option. ABCO requires a maximum cycle time of 7 seconds. If I can test at a 5-second cycle time, that'll provide a good safety factor for the requirement and add some wiggle room for the as-built unit. Setting the cycle time is easy. Here I've defined the movement of the arm by splitting the motion into time segments. As the arm changes direction, SOLIDWORKS Motion adds a cubic interpolation to smooth out the movement. Doing this by hand would have taken forever. With the PathMate motor all set up, it's time to solve the simulation. Perfect, that's exactly what I was going for. I now understand the desired cycle time, but this is just an intermediate result. To calculate the torque requirements, I'll need the time-based angular position of the shoulder, elbow, and wrist joints over the complete cycle. For that, I'll plot the projection angles versus time for each joint and save as a CSV file. Now, I'll create a second simulation and use inverse kinematics to solve for torque. I'll start by suppressing the PathMate. I won't need it since the pick and place mechanism will now be driven solely from the angular position versus time data solved in the previous study. Next, I'll add a motor at each joint. I'll start with the driving face of the shoulder and import the CSV file as the motor input. I simply need to repeat these steps for the remaining 2 motors. And I can't forget to turn on gravity to simulate the real-world physics of this mechanism. I'll create a torque plot for each motor, which gives me a complete time history. Looking at the shoulder motor, it shows a max value of nearly 1,100 inch-pounds. In this configuration, that servo motor alone may cost as much as our bid for the entire job. I don't want to break the bank on expensive motors, so I'll need to discover some new ways to tweak the design and reduce the overall torque. The maximum torque of the shoulder motor occurs right as the arm picks up the soap bag from the conveyor. Moving the mounting point of the motor closer to the conveyor may reduce torque, but randomly moving that mount location is just a trial and error approach. Instead, I'll use a design study to solve for the best mounting location. If I can balance the required torque to pick up the soap bag with the torque to place it in the box, overall max torque will be reduced. Using a design study, I'll incrementally change the mounting point location while recording that all-important distance variable. Scrolling through the results, I can see the center of mass distance is nearly identical when the mounting bracket is 37 inches from the far end of the frame. That should help. If I lower the mounting point of the motor on the frame, bringing the motors closer to the work, I may be able to further reduce the required torque of both the shoulder and elbow motors. A simple sensitivity study shows that lowering the mounting bracket just 3 inches will further reduce torque requirements. I'll change the dimension of this mount mate, but not bother changing the geometry of the frame. That'll be Jordan's job. The optimal length of each link can also be solved with an additional design study. It turns out that the best configuration is for each link to be identical in length, 13 inches long. Reducing the amount of unique parts should make Brian happy. I'll run this new configuration and solve for the projection angles and torque values. Wow, that's a reduction of over 40% in the maximum required torque. Using an inverse kinematics approach, SOLIDWORKS Motion provided insight into our design, and I made some simple geometry recommendations which will reduce the torque requirements of the pick-and-place mechanism. Brian's going to be relieved that we can utilize smaller, less expensive servo motors and preserve the already razor-thin budget.